Hello, this is Daryl Corn, and this is my video walkthrough of my midterm exam for Intro to Machine Learning. Let's start with looking at the code for question 5. So within my code, I first I search for some random forest hyperparameters using the n estimators and maximum depth. We find the best combination there. And then using all of those tests that we just ran, we can plot the results on a graph. So here the different colored lines are the different amounts of estimators. So 10 estimators is blue, yellow is 100, and red is 200 estimators. So we will explain that more in the table 5 or question 5 explanation. Train on the full data set there. Here we're looking at misclassified samples from the random forest. Here is the feature importance graph on the 8x8 graph. Then we get into the support vector classifier. So we can choose to scale or unscale the data there. Here we are searching for hyperparameters with c-values and kernels. And similarly to the random forest, we then plot the different values here. You have to run it twice, once for scaled and another for unscaled. And then you can train on the full data set using the found hyperparameters. Then we look at misclassified samples yet again. And then here we are comparing our final best trained models. Here's the probability scatter plots for classes 0, 3, and 7. And then finally, we look at the group 1, 2, and 3s for the different probabilities. So now that we've got all of that, let's talk about these homework answers. Okay, so for question 1, question 1 asks us to create a two-dimensional data set with some samples and then compare regularization on them. Yeah. So when I created this distribution here to show where if you don't use regularization, it's this dashed line here, you can get 100% accuracy on it. But if you add regularization, it's going to move this decision boundary to this wider gap here, this dotted line. They look kind of similar. My apologies. I'm just now realizing that. This dotted line is with more regularization because it's a wider margin between these samples. But it's going to misclassify these two X samples here. So one for part A here, one reason you might prefer the regularization option, the dotted line here, is because that may generalize well to in deployment, because you might see some unforeseen data, and you could get a higher accuracy using this. But if your training data does represent everything you're likely going to see in deployment, then for part B here, you would actually want this highly accurate without regularization model, because that does give very accurate answers. So on to question 2. So question 2, I spent a lot of time on, and I believe it is not possible to create a data set that performs well with decision trees, but not with MLP, SVM, logistic regression, or k-nearest neighbors. And that's mainly because you have these 3 qualifiers in the question. So 1, the data must not be linearly separable if logistic regression is not performing well. If k-nearest neighbors doesn't perform well, then there must not be any obvious clusters within the data. And lastly, if MLP and SVM are not performing well, in their simplest versions, they are just linear classifiers. So that puts them with logistic regression over here. But the question didn't really mention any restrictions on them. So if you allow them to become more complex, then they find these non-linear separations in the data. And if these are also not working well, then it must not be easy to separate these classes with a nonlinear decision boundary. So it appears we have a really complex data set here. And I just don't think it would be possible to expect a decision tree with only a max depth of 2, which keeps it at a very simple level, really, to outperform all these other classifiers. And I drew this explanation here. This is like the closest approximation I could really think of um, for the decision tree. But if you kind of drew the data out in this checkerboard pattern, then that gives you this data that it can't be linearly separated. And the decision tree, because it has a max depth of 2, it can draw these 2 lines that are vertical or horizontal. So we could split these and get 100% accuracy. But there are still these very obvious clusters that are remaining. And if you allow MLP and SVM to have no restrictions, then it could probably find a nonlinear separation here as well. So that's why I think it's not possible to generate data that all samples can be correctly classified with the decision tree, but not with all these other classifiers. Okay, on to question 3. So question 3, what was that one asking? Large data set, and case of underfitting, what can you do? Okay, so one strategy if you are underfitting with logistic regression is that the model might not be complex enough. So logistic regression finds linear separations, and it requires the data to be linearly separable. So a more complex model, such as SVM or MLP, or even a decision tree with a depth of more than 2, or k nearest neighbors, they may be able to find these more non-linear patterns within the data. And the way that some of these are able to find these more complex boundaries, the SVM model uses the kernel trick to kind of abstract the data into much higher dimensions, and it may be able to find a clear decision boundary up there. Or for MLP, if you give it enough hidden layers, it can find this very complex nonlinear decision boundary. So those are 2 possible options if logistic regression is underfitting. Alternatively, you could try to transform your data so that logistic regression is better able to find a linear separation. And one way you can do that is using principal component analysis to kind of merge one of these dimensions into another, thereby instead of having 3 dimensions, you would have 2 dimensions, but you do get to keep the same amount of information within the data set. So after doing that step, the logistic regression may be able to find a better linear decision boundary. All right, question 4. Question 4 is about overfitting with MLP. So when the multi-layer perceptron algorithm is overfitting, one reason it might be doing that is because the model has a very large capacity to learn the data. So you could try to reduce the size of it by reducing the number of layers in the model, or maybe the number of nodes per layer, or maybe even both, really. So if you have a lot of these layers and nodes, it allows this multi-layer perceptron to find this really complex decision boundary in the training data, and it fits very well to the training data, but it might not generalize well to deployment or test data. Another way to try to improve the overfitting would be to increase the alpha parameter within MLP. So this alpha parameter controls L2 regularization, which kind of shrinks the weights of the model towards 0. And that prevents the model from making these large leaps and changes to fit to the data. And it just, the weights move more gradually and don't really fit to the noise as much. So it could make a more general decision boundary that fits better to test data. Okay, on to the big one, question 5. So part one, looking at the random forest classifier, I found that the optimal parameters were a max depth of 7 with about 200 estimators. Like further increasing the estimators just kind of slowed stuff down and didn't really improve model performance. And we can see that we start to overfit around max depth of 10 because now we are like memorizing training data at 100%. But really anything before 7 or so around here, it it's still underfitting. Like we can still get better model performance. So same with the less estimators. At 200, we kind of have our peak, but the less estimators were still kind of underfitting because we could be getting better performance still. Looking at the misclassified samples, there weren't very many. Some didn't have two misclassified samples. Some classes, such as class 3, didn't have any misclassified samples. And some trends here, it kind of seems like it's struggling on these more messy numbers, which is fair. Like number 4 here, that's hard for us to discern, really. But also, these numbers tend to have a lot of slant to them, which I think is confusing it. Like this slanted 8 kind of is looking like a 7 to it. Same with this slanted 9 and this one. So I think that is a factor, as well as some of these seem to be off center, such as this 1 here. So I think one way to help this would be to kind of randomly rotate and transpose training data. Just a thought for if someone really needed to tune this model. And part C is to create this feature importance heat map, which I have here. We can see that all of these numbers are pretty well centered because anything in column 0 and 7 has very low importance. But one area where it's very high importance is pixel 5.2 here. So this must be it must vary a lot and is a quick indicator as to what kind of number it is. So maybe numbers like 5 or 6 have this blank, but 7 and 9 are always going to have this particular pixel. So that could explain why that one in particular is so important. And some other ones that are very important are these in the center. It seems to be where, as I put it right here, digit shapes differ most distinctly. All right, on to part 2, the support vector machine classifier. So this one, I found that unscaled data seemed to be the best. I think that's because the data is already fairly well scaled. So scaling it again is kind of redundant, and we actually lose a little bit of data in that process. And I also found that with unscaled data, a C value of 4. So a good bit of regularization on the model really helped improve it. And we can see that we are underfitting for quite a while with too much C before it jumps up, and then it quickly starts to memorize the training data around C is equal to 1, and especially by C equals 10. So a C of 4 on unscaled data proved to be the best performance. So for the misclassified samples here, it missed much less than the random forest, and actually you can find all of these samples in the misclassified samples of random forest. So clearly there's some difficult, messy samples. And I feel like I see a similar pattern where these are some fairly slanted numbers, and maybe the model could benefit from more varied data that are rotated a little bit. All right, part 3, we're going to start comparing the two final models. So here I have the scatter plots depicting the different confidence levels of the classifiers on some samples. And we can see that the support vector classifier is a lot more confident than the random forest, just because we have the spread, like this horizontal spread of scatter points, but we don't have so much of a vertical spread. Class 7 has one sample here in the middle where I guess both classifiers were a little unsure of it. But for the most part, stuff is gravitating to the corners of our graphs, which show that the models are pretty confident on a lot of these samples. Now, to kind of dive into these individual groups for the classes and compare the confidences. So group 1 are samples that are easy to classify for the support vector machine, but harder for random forest. So these are all ones where the random forest did not do particularly well, but the support vector machine got it. And a lot of these we saw earlier in the report. It seems to me that these samples kind of have a slant into them where they're running from this top right corner down to this bottom left corner. So I think that's starting to throw the random forest for a loop where the support vector classifier may not be confusing those as much. That seems to be one pattern that I see here in group 1. So for group 2, this group's actually empty. We didn't see any misclassified samples from the support vector machine that the random forest actually got right. So there's nothing really to show for this one, unfortunately. But lastly, for part C, where both classifiers were unsure of their classification, we do have these 4 samples. And I think that's just showing that these are very messy samples that would be hard to discern, probably even for a human, honestly. So you could tweak your model to really fit these, but the fact is that these samples may just look more like other numbers. So you might not want to have your model classify these correctly and then perform poorly on deployment data. So I think it's a case where accepting some mistakes is okay for this. Okay. Well, to conclude this, I think the support vector classifier would generalize best on the test data. The model was highly accurate with 99% on test and training data. It was interesting that the model didn't benefit from scaling of the data, but I think that is just because the data is already scaled, so it was kind of redundant. One drawback to the support vector classifier is that it's not as interpretable as the random forest. Random forest has the ability to generate those feature importances, which is very neat. But random support vector classifier, it does have the ability to at least generate probability statistics for each prediction, which can also be useful if the user wants to review less confident predictions. So I believe that concludes my midterm exam video walkthrough. Thank you.